I do have the video loading on YouTube right now. It'll probably be loaded, ready to go for you guys to view for the afternoon session from yesterday. All right, so we have signal flow today, better known as the transmit path and the receive path. These are going to be coming from your electronic C's and D's. If you pull up your tech order for the Jerk 239, they're also in there, but you got to tilt your head sideways in order to see them. What we did is we took those pictures and laid them sideways so you could see. Also, in the testing lab, you will be given a disc with the NSM-TO. You'll be given also the electronic version of the tester TO, Jerk 239, and the electronic version. But if you prefer paper, there is the paper copies of the electronic version of the C's and D's. Highly encourage you to use those if you want. We have the Baseband Assembly, and this is picking up in paragraph 5.2.2.1 all the way through 5.2.2.3. This is what it looks like in full color. So we're going to refer to this when we go to parts on the TO. So we will be coming back, so watch what I do as far as flipping back and forth and referencing anything. Now, for some reason, I don't have a pointer, so I'll do my best to get you to, when I go to this, I'll probably download an arrow and put in there. So the place that we're going to start is on page 4 and 5. 4 is the baseband transmit signal flow. We're going to be following the bold lines. We're also going to be going with the adage that our operate switch is in, or our standby operate switch is in operate mode. And what does that mean? Well, if you look back here, we grab an arrow, and I'm going to move it all the way over here. This is where your standby operate switch is, and it's in operate. What does that mean? It means that you are now transmitting out the antenna. So, without further ado, we're looking at the bottom right-hand side. Gotta love these arrows, right? Woohoo! Yay! This is where mission traffic is coming in. It's on the back of our baseband assembly. This is where a multiplexer is going to come into. This attenuator that we're going to go through, now watch this. The attenuator that we're going through is here and here. You'll notice that this one says 0 through 20. The other one says 0 through 10. For example, right now, if you were to take a look at it, this arrow right here is pointing to the 20. Well, you have 20 dB of attenuation, and you look at this white arrow right here, and it's pointing to the 10. That means you have 30 dB of attenuation. So with that in mind, if I told you that I wanted 15 dB of attenuation, I would pull this 0, 10, and 20 to 10. I would come down here and twist the knob to 5. That would give me 15 dB of attenuation. So you can see, reading through the tech order, that we have that attenuator is going to set 3 volts peak to peak. It's going to be 30 dB of attenuation. The idea is to get it down to where we see it in the meter in green. Let me go back up here. See the little green on our meter? Well, we're going to get that needle right in there by using the attenuator. Now, when you guys are in the Tisser lab, we are pretty much going to be non-existent with that. It should always be in the green because we don't have a multiplexer to tie into it. But if you did, like the FCC 100 like we had, you would automatically have to turn it down. We have a baseband filter. This notch filter is 8.5 to clean it out. In other words, nothing at 8.5 megahertz is going to get through. Now, let's go back one and look at that mission traffic. The mission traffic is nothing more than the pseudo NRZ or the CDI. Orderwire comes in later. Now, that is what the multiplexer is giving us coming in. And when it comes through this baseband filter, there's really shouldn't be anything on the 8.5, so it's going to clean it off. Now, please understand, this is an aggregate going at that, I think it's 72 to 4668, and the other one is 6448 meg. 6.4, the other one's like 4 point whatever, and so the 8.5 is not even going to affect those two. So it cleans that out, and there's a reason why. When we get to the summing buffer amplifier, we are going to clear off we are going to combine the mission traffic, which one of those two that you're going to have coming in, with the order wire signal. Now the order wire signal is at 8.5. Now you understand why we had to clean it off down in the lower end, is just in case there was some noise and crap on it. So when our subcarrier at 8.5 comes in, and that's the order wire, we're able to combine the two through this amplifier. Now it says summing buffer amplifier. It's been my experience that when I combine two signals together, it's a common base with a unity of 1. What does that mean? It means I'm able to combine the two. If there's just a little bit of variance, it's not going to be too much. And I'm talking variance on power. We're going to be able to combine these two. And what it means by a unity of 1 is there's really not any amplification, but there's no degradation. That's the key part. No degradation by combining the two signals together. So at this point, you're going to have, coming out of that summing buffer amplifier, you're going to have mission traffic and order wire. We're going to go through something called a Diplexer, wherever you heard that from. This is a passive device that's going to use filters pretty much. The idea behind this Diplexer is we're going to have a combination on one side of the Diplexer, and then on the other side we got to separate them out. One's going to be a transmit baseband, the other one is going to be a 70 megahertz IF signal. So you can see why we have that Diplexer in there, to make sure that the 70 megahertz goes where it needs to go, and the baseband signal needs, where it needs to go. So that's what the Diplexer does for us. And of course, this is giving you an idea what a Diplexer is. Now, when it goes out of our baseband assembly, it's going to go on a 2-foot cable or the 150-foot cable. It is a Canon plug, and if you take a look at the plug, either side, you will see that there will be a very small RF cable in there and a whole lot of other pins, so to speak, that if you were to section all those pins out, you would be able to see a lot of control, power, things like that that's on those pins. But it's the RF that is transmitting, or the coax cable is transmitting the baseband and order wire, as well as the 70 megahertz on that cable. We're going to come out of the back of the baseband and into the RF assembly. This is what the RF assembly looks like. You can see that we have frequencies, and I'm going to point this out to you. When you get your cut sheet, you're going to be in, it'll give you the transmit frequency first and the receive frequency second. In the tech order that you will be given, because it's an extract, because it doesn't make sense to give you the whole thing, it'll tell you to enter in the frequencies. That's all it's going to tell you. And the idea here is you're going to go to that cut sheet, you're going to enter the frequencies on the thumb wheels. Again, the 1 is what we call screened in. It doesn't change. And this is going from left to right. And that's the tens of gigahertz. The ones of gigahertz will only go between 4 and 5. Now, there are some, because we can't get the thumb wheels anymore, that they will be locked onto either a 4 or a 5. So depending on the equipment that you get, you might be able to have a piece of equipment that's working with the 4 and the 5, or you may not, and it'll have a little sticker at the top saying, hey, it's locked onto 4 or it's locked onto 5. The last 3 digits from left to right, you can change to whatever. If you change them out of the frequency range of the tisser, you'll get a channel error light. You will also get a summary alarm. Excuse me. But entering in those frequencies, changing gears now again, when you enter the transmit frequency, it's on the bottom. So if you look at that front panel, transmit frequencies are on the bottom. The receive frequency is on the top. But, and I see this often, left-hand side bottom, there's a knob. It also says receiver frequency. Please remember to turn that dial also. Because when you go into operate and you're trying to figure out why it doesn't work, well, there you go. You probably didn't turn that receiver frequency where it should be. Or another one that often happens is you'll put the transmit frequency in the receiver thumb wheels and the receiver frequency in the transmit thumb wheels. Happens all the time. So I'm just giving you a little pointer here when you finally do get to go to the Tisser lab. So that way when you start working on it, you don't fall into the same problems that we've seen in the past. So when we come out of the back of the baseband assembly into the RF assembly, we're going to come all the way up to the Diplexer. Again, this is going to keep the IF separate from the baseband and Orderwire, so it goes in the right direction. Again, there's your Diplexer. We have an amplifier. That's the first thing that's going to go into, and there's a reason for that amplifier. You really don't need to amplify a whole lot if you have the 2-foot cable. However, if you have the RF device mounted, let's say 150 feet away from the baseband assembly, or it's up on the mast, or it's up on the pole, 150 foot, you're going to need to do some amplification. It's going to compensate for that long length of cable. We're going to use something called a transmitter encoder. That's the thumb wheels. It's just another name for it. And it's going to send out a binary coded decimal signal, 1s and 0s, to the phase lock loop. But when it does this, it goes through something called a data switch. This data switch is extremely important when the standby operate switch is in operate. When it goes into standby, that data switch does something a little different. We'll get to that when we get into loopback. So the data switch is going to pass the BCD over to the phase lock loop. Now let me grab an arrow here. This arrow, you can see here's phase lock loop. It's going to come down. It's going to give us a voltage. It's going to come up to our VCO. The VCO is going to generate a frequency. At the same time as it going to the multiplier, it also comes up into the divider. And what it does with this divider and that divider is it brings it down into a number for the phase lock loop to compare with the encoder. If the phase lock loop and the encoder match, nothing happens with the phase lock loop as far as voltages are concerned to the VCO. If we're too high, the phase lock loop is going to send a voltage to the VCO and tell it to turn down the frequency. If it's too low, it's going to make that circle again. The phase lock loop is going to compare it with the transmitter encoder signals. If it's too low, it's going to send a different voltage out to the voltage controlled oscillator. That's how phase lock loop works. But you'll also notice that we've got a big blue box around the VCO. Remember our simplistic radio in transmitting baseband to the distant end? The first step was modulation. There you go. So we're highlighting modulation to give you an idea of what's happening. Copy this. So this VCO is going to generate a frequency of 7.2 to 7.625, I think. And what it's going to do is it's a representative of the VCO or the encoder, and it's also a discriminator. This discriminator does the modulation. You can see it right there. It does frequency modulation at the 7.2 to 7.625. You're going, well, wait a minute, in frequency range 14.4 to 15.25? Yeah, it is. But we're not there yet. Remember that little thing where we take and we modulate it going from baseband to IF? There you go. That's IF. That's an intermediate frequency. Remember back in a couple other slides, back in, I think it's 3 alpha, where we talked about the IF being anywhere between 70 megahertz to 30 gigahertz. Again, it depends on the equipment. So we get this at 7.2 to 7.625 modulated in the FM. We go to a multiplier. There's our second step. We're going to take our IF and go to RF. The way this multiplier works is it's an amplifier. Wait a minute. It says times 2. Au contraire. Electronics are funny like that. They always give it names which are sometimes misleading. But when you finally understand it, what this amplifier does is in FM, when you amplify an FM signal, it generates something called harmonics. Now, for those of you who've been in band, harmonics is a harmony and multiple of frequencies where it sounds really good. But with a harmonic of 7.2 to 7.625, that is our first harmonic. Our second harmonic is, oh, look, 14.4 to 15.25. So what we're going to do is we're going to double this in a harmonic way. We're going to run it through a filter and select that second harmonic. Everything else goes away. Now, I've worked with radios where we use either the second harmonic or the fourth harmonic, and it is quite unique in how you got to set that up. We also run it through our final stage, which is RF amplification. So right away, we've done what the basic radio has said. We have modulated it, changed it to IF, IF to RF, which is the up conversion, and then RF amplification. We just satisfied those 3 steps of transmitting baseband to the distant end. Now, this particular amplifier is called a field effect transistor, normally anywhere between 4 to 6 leads. It generates a lot of power. Now, in our case, we're probably talking down in the microwatts, and it's going to go from microwatts to milliwatts. Now, that's a pretty significant change there. We're looking at 25 dBm. Now, look what happens next. We end up in the branch assembly. Oh, where have you heard that one at? So, it's kind of unique. Again, we're taking you through the basics of the radio, but we're being able to identify it on the tisser. So when we run into, oh, I can't believe I suckered myself into that one, an isolator. What does an isolator do? Separates the RF from getting back into the system to damage the equipment. We want it to go one way. In other words, if there's reflected power coming back, we don't want it to get into our electronic section. So that's what the isolator is doing. We're going to run into a harmonic filter. Remember that when I said that the FM generates a lot of harmonics when we amplify it. Again, clears them out. We select the ones that we want. We're going to end up going through a circulator. Up here for just a second and drag this down. Whoa, a little bit too much there. So we have a circulator. See the next one right here. Harmonic filter. Yep, there we go. We got it right. Into the circulator. This is going to route it. You'll notice right away that it can only go in one place. You're going, wow, how's that possible? Your internet just cut out. Wow. I was at 920. Smith, are you still there?
Yes, sir.
Okay,
I connected it on my phone while I try and fix my computer.
Okay. And again, if you're missing stuff, thank you for letting me know, though. I'm sorry I didn't see it fast enough, but you got the video when I get it up and operational. Hopefully it'll be later on today. All right, the transmitter circulator, you'll notice it can only go one way. Let me grab or paste my arrow here. Okay, it goes this way. You'll notice we got a transmit, standby relay. It's closed, so it's going to come up to this other circulator. But look where it could go. Well, if it comes up here, goes through our pre-selector filter, through an attenuator, but when you get up to here, it has no place to go. So path of least resistance is going to go this way. So the 3-port signal isn't really going to help us out. Again, this is a circulator. We're going to go through this transmit standby relay. This will go a different route when we are in standby. But in this case, we just follow the bold line because the switch is in the down position. We go up through the other circulator. Again, 3 ports. This one does the big job where it's going to select the transmit to go out the antenna, and at the same time it's going to let the receive come in the other side, or the same port, but it's not going to let it get into the transmit section. It's going to let it go through the receive section. It will not let the transmit section go in through the receive section. Yeah, and it works off of impedance. And then, of course, when we are transmitting out, goes out through our dish. So we're going to do the reverse. We just went over transmit. Is there any questions on that one?
No, sir.
No, sir.
It's one of those, if you follow the TO and just follow the bold lines, you should be able to decipher some of this stuff. I'm just trying to give you guys a little bit more understanding, because in the tech quarter, sometimes you have to read it 3 or 4 times just to get the idea of where the heck it is. All right, so we're off of page 3 and 4 now. We're just going to be 4 and 5. Now we're going to 6 and 7. Page 6 is where we're starting. It is the RF assembly, and then when we get out of the RF assembly, we'll go to the baseband assembly. Let's start. This is our front panel. Again, it's blown up for you. We'll be referring to that on occasion. Again, we're part of the receive branch assembly. We're going to receive the signal and follow the bold lines in this case. Again, going through a circulator. Comes up to our standby relay. It can only go one way. Into the pre-selector filter. This pre-selector filter is this device right here. This is what I'm talking about right here. They call this a cat's eye right here. And you're going to adjust this knob to the receive frequency. So that's what you're going to be doing when it says enter in the receive frequency. You're going to put the receive frequencies in the thumb wheels here, and then you're going to come down and put the receiver frequency by adjusting that knob here. Whatever the receive frequency is, you're going to put it in. Then we go through an isolator. This is to keep the RF from going, because your mixer is going to generate RF. It's wanting to get out also, so we need to put it one way and one way only. So that's where the isolator comes in. So now you've gone through the bulk of the branch assembly in both transmit and receive. So the first place that we're going to go, and you've seen this before, the object of receive is to recover the baseband. It does it in 3 steps. Here's the first step. So we're going to take this signal and we're going to amplify it. If you hadn't noticed, all of our amplifiers are triangles. So and it has L and A in that little box. So you're going to have RF amplification, and it's enough to pull the signal up out of the dirt, which is what I like to call it. In other words, then you're going to have noise and you're going to have the signal. So you're going to pull it out of the dirt. Normally it's around negative, good grief, anywhere in the negative 90s to all the way down to negative 120, depending on how well or how good your receiver can pick it up. Okay, this section right here is considered the down conversion portion. So hopefully you can understand that when we go through this, there is a logical sequence of events that happens to get it to the down conversion. Again, it relies on a mixer, not a discriminator. This mixer works off the word heterodyning. Everybody remember that from Dolan Hall?
Yes, sir. Yes, sir.
And
it's what happens in a multiplexer.
A multiplexer?
Or not a mixer.
Yeah, that's much better. Okay. And what did they tell you about the mixer when you do heterodyning? What are the signals that are coming out?
It's combined IF and the carrier frequency.
Well, I don't like the word IF. Okay, so let me back up here. Grab an arrow, hasten the crap out of it. First of all, you have RF coming in, the receive frequency, and it gets to the mixer. Okay, you need 2 signals in order for it to mix. 2 unlike signals. They have to be different. If you had two of the same, it won't work. This encoder is going to generate, or excuse me, tell us what the phase lock loop, which works down like the same exact way as the one below it, tells the VCO what to do, multiplies it, filters it, and the TO reads, I remember looking at it yesterday, it says that whatever you have on the thumb wheels, that's these, the transmitter encoder, it will be 70 megahertz below the receive RF frequency. That's what it says. 70 megahertz below the RF frequency. So when you combine them, coming out of that mixer, you will have the two original frequencies, which is the RF and the transmit encoder. You will also have the sum and the difference. All right? So I'm just going to pick a number just to give you an idea. 15 gigahertz, because that's well within the frequency range. I got 15 gigahertz coming in here. I will have 14.93, I think, gigahertz coming in from the VCO side. That's the oscillator. When I come out, I'm going to have the 15, the 14.93. I will have the sum, which will be somewhere around, 39 and change gig, and the difference, which is anybody? What's the difference?
One more time, sir. I couldn't hear you.
Okay, what is the difference? In other words, we've gone through and determined what the two originals were. What is the difference? We've also looked at the sum. The sum is around 39 point whatever gigahertz. What's the difference? Here, I'll even give you a little hint. Let's see, it should be up in here somewhere. Doesn't have it? No? That's interesting. What's the difference? Right there on that page. Nobody knows.
You're talking about the 70 megahertz of the down conversion IF?
Yeah. That is what we want, the 70 megahertz. So those are your four frequencies. You had the receive frequency, you have the oscillator frequency, and then when you mix those two together, you have the sum at 39 and change, because we were using 15 gig, and we have the 70 megahertz. How did they get the 70 megahertz? Well, the encoder told the phase lock loop to do 70 megahertz below the operating frequency. Okay. Good catch. Okay, we take these four frequencies, we amplify them. We run it over to another amplifier. You go, well, why could we just amplified it? Well, there's a reason why. When you have all of these frequencies that have been manipulated, you want to gradually bring them up, because if you just amplified them in one mass amplification, you run the risk of generating more noise than you do the strength of the signal. That's the reason why we gradually bring it up. Kind of like, no, I'm not going to get that analogy in there. So we have four signals being amplified, but here is where the last part, where everything gets weeded out and we can say we now have the 70 megahertz. That's the reason why I use this for the down conversion. because you still have the original frequencies, but it isn't until after the bandpass filter. Now, where is the 70 megahertz made at? Anybody have a clue? Take a wild guess. Where's the 70 megahertz made on that line?
That's a bandpass filter?
Nope. The bandpass filter eliminates everything except the 70 megahertz. But where is it developed?
Oh, the low noise converter.
Low noise converter. Okay, you're getting close, but what component?
The microwave LRU?
Well, it is in the microwave. You know, I'm talking component. It was within that low noise converter. You got a choice of 3. Wouldn't the image reject mixer do it? Yeah, because that's where it's made. In other words, it's taking the sum and the difference in the 2 operating frequencies that are coming out, so it just made the 70 megahertz. So that's where the 70 megahertz is made, in the low noise converter, in the microwave LRU. And good job on identifying the LRU. So now that completes the down conversion. So we had RF amplification, down conversion. Now, anytime we manipulate the signal, like running it through a filter or a mixer or anything like that, we're going to amplify it. Now, this one is considered an AGC amplifier because we're going to look at the received signal strength and adjust accordingly. So you could actually have some gain in here. We're going to run it through a Diplexer. Again, it keeps everything separate. You know, it combines both on one line, but at the same time it separates, in this case, the 70 megahertz receive from the transmit. We're going to run it out the RF assembly off the back and run it into the baseband assembly on the back of it. Here is your baseband assembly again. We're going to show you some points on that. That's the reason why it's blown up a little bit. We're going to run it through a Diplexer. Again, separates everything. Run it through a cable AGC. Now this one is if you are running it through the 150 foot, you're going to have a lot of amplification. If you're running it on a 2 foot, there's going to be minimal amplification. We're going to run it through an IF demodulator. This is going to take our signal and we're going to have 2 off of it. So 70 megahertz is being put into where we got 2 signals. You're going to have Orderwire at 8.5 and you're going to have the mission traffic. So those are 2 separate signals. We're going to run it through this whole section here for demodulation. Now, where demodulation happens, the IF demodulator. It is a discriminator. Again, it's going to take it because it's FM and run it into the mission traffic and order wire. It doesn't. Now this is where things have to get weeded out because you have mission traffic and order wire. You can't have both on the same line. So this is where we get into some technicalities, and if you read the tech order, it says the low pass filter passes mission traffic. Well, with filters, there's always a problem with it. The idea behind this particular filter is we don't want anything residual from the 70 megahertz getting through, because sometimes 70 megahertz will actually bleed through lines and get into something else. So that low pass filter truly prevents the 70 megahertz from getting through. It also is responsible for starting to get rid of the order wire. Does that roll? Starting to get rid of it. Okay? It may take out some of it, but it doesn't take out all of it. It takes out all of it here. At this point, it is true mission traffic. That's the reason why all 3 of those are in that little blue circle to say, hey, this is our demodulation. So the idea is we don't want any other signals other than mission traffic to flow through it. In the TO, it will tell you, hey, low pass filter in the subcarrier notch, and it will lead to some confusion, but it isn't until you get to the subcarrier notch where everything is weeded out. We have something called an FOGM interface. This is a switch on the front panel. Let me go to it. It's right here. There's your GM FO switch. We're also going to run it through a receiver baseband attenuator. This GM FO is GM's group modem, which is CDI, and fiber optic is a pseudo NRZ. Okay. Next up is the attenuator. I just showed you that. And the whole idea here is to get it at 3 volts peak to peak. Now, the reason why it doesn't have from 0 to 30 is because when you get the RF signal coming in, it should already be very close to the 3 volts peak to begin with, but as you amplify, it may increase. So there's very little attenuation that is needed when you're dealing with the attenuator on the receive side of the house. That's the reason why the differences. Okay. Orderwire. This is always a fun one. In the world that I got 2 of these. Yeah. Sometimes I get a little overzealous when I'm making some of these slides to get them explained. So, Orderwire. This is on the, you can pick and choose whichever one you want. This is the C's and D's from the tech order. We did not supply them for the C's and D's on the electronic version because there's very little that goes through this. You'll notice that I have a, oh my, little, we're going to start right here. Let me try to explain this to you. All right, on the baseband assembly, on the rear of it, there is a connector for the handset. In other words, a telephone-looking device that has a cord on it. This is the connector for it. All right. So what happens is, you got it connected, you speak into it. Okay. You can follow the arrows. Goes through the Orderwire interconnect intercom, comes through the bold line, down, and into the transmitter subcarrier generator. This device converts our analog or digital voice Orderwire into an 8.5 megahertz FM signal. It comes over to the summing buffer amplifier and is combined with the mission traffic. That's the reason why this is a key ingredient when you are talking mission traffic and Orderwire. It combines the two without too much of an issue. When I say too much of an issue, is you got FM on one side, which is at 8.5, and the max on your mission traffic is 6.44 meg. So you can see that they're close, but they're far enough apart. One is FM, the other one is a digital signal. When you have the return of this, in other words, if you're talking to someone in the RF section that's outside, or if you're talking to the distant end, when it comes in on our receive side of the house, comes up, goes through here, gets demodulated. Well, you have mission traffic come down here, but when it gets demodulated, it only demodulates the FM portion, and it stops the mission traffic. It doesn't go anywhere because the impedance of the circuit prevents it from getting out. So now you have voice coming down this line through the Orderwire interconnect, through our connector, and to your handset receiver section. That's how Orderwire works. Everybody get an idea how it works? No, maybe? And this is straight out of the tech order.
Yes, sir.
Okay, so,
I'll definitely need to watch the video again.
okay, yeah.
I'll need to
well,
go over it.
you
So
want me
what's the modulation technique for the order wire?
FM? Kind of crazy when you think about it. Let me go up here to the this section right here. Come on. Let me take this, click it out. How hard is it to delete? There we go. Do a paste. Oh, crap. That's not supposed to do that. Here we go. Let me grab another arrow again. All right. When Orderwire comes in, it's on the same line as baseband. Okay, comes up, goes into your Diplexer. Now this is a received path. I just grabbed it real quick. We're going to take this and run it through. It's amplified up on this line and gets modulated with another FM signal. It can do that. The difference is you got an 8.5 and whatever your mission traffic is. When it hits this VCO, that is a discriminator, and it will combine it into an FM signal. It's two carriers being put onto another carrier. So it's kind of crazy, I know, but it gets put on there and then goes out through this way and then out through the antenna. That's how the order wire flows. So you actually have, that's the reason why it's called a, really? Okay, good. Back down here to my order wire. This is the reason why this is called a transmitter sub carrier generator. Sub carrier, because the main transmitter is in the transmit section on the RF assembly. I had that same question as how can two FM signals be applied, and then they explain it that because of you having two carriers being put onto another carrier, it's able to do it. Remember now, FM, you can have multiple frequencies on it. Kind of crazy, I know. Okay, so clear on order wire.
Yes.
Okay. This is what the order wire does, but I want to point out one thing here. Order wire intercom switch. This is always a fun one. Go back up here, see if I got my arrow. Nope. Undo that. Grab an arrow, like this, just copy that. Come up to here, paste it. Okay, this switch right here, the intercom order wire. Let me try to explain it. Intercom means that you can talk between the baseband assembly and the RF assembly. No one else. Okay? Once again, intercom between the RF assembly and baseband assembly. The moment that you switch it to Orderwire, this switch should be in operate. You can now talk to the distant end. Both of you can. Both the RF assembly and the baseband assembly, as well as talk to each other. Yes, on both sides. So if you can only talk to yourselves and you're trying to talk to the distant end, look at this switch. It's probably still stuck in intercom. When you flip it in the Orderwire, and this is in operate, you can talk to the distant end. You can talk both to the RF assembly or the baseband assembly on the distant end. Same with the distant end talking to you. And of course, you can talk to, if you're on the baseband, you can talk to the RF and vice versa in this position. Operate in Orderwire. It will tell you in the tech order when to switch it out of intercom and put it into Orderwire. On occasion, people miss that step. All right. Transmitter subcarrier generator again modulates analog voice with 8.5 megahertz Orderwire subcarrier. It is an FM signal. It says it right in the tech order. Test tone oscillator. Again, there's that safety tip again. Do not have the headset on your ears when you get to this point. It's not helpful to your hearing. It'll blast you. There is no volume control for this signal. One of the most irritating frequencies to me. Oh. When we were in Jones Hall, I'll be teaching a class and all of a sudden I'll hear it and it's like, okay. And then it's constantly going. So I go find the instructor and say, hey, is there any possibility that you can tell them that, hey, hear the tone, switch it off, please. It's one of the most irritating tones out there. And you thought that, the 1 kHz tone, this one's worse. Well, anyway, trying to get at it, test tone oscillator. What it does is it says that when you generate this tone, your test tone lights will illuminate. Let's go up here. All right. Here is your test tone. You have baseband, you have Orderwire. Why? There's your test tone light. Here's a test tone light. You're going to be able to check these two as to whether or not that you're able to generate a test tone in Loopback. Caution. Do not have this switch in either baseband or Orderwire when you have this switch in operate, because the distant end will probably be cussing you out. You're generating a 2.6 kHz tone down to the distant end. Just saying. Gotta love these switches, eh? By the way, here's your speaker. You'll notice that this says on and off. Here's your volume for the speaker. Notice that there's no volume control for your handset or headset. What else do we got to go through? Standby loopback. Ah, yes, the fun stuff. Again, this is taken from your tech order. It does go through standby loopback. This is your signal flow. When you are in operate, you're going out the antenna. It works differently when you are in standby. It generates something called a loopback. How does it work? Well, we start with the receiver encoder because it's going to use this as our, the receive frequency. But one thing I told you about, and here's where that data switch comes into significance. You can see that right about there, there's a little word called standby. This is controlled by the standby operate switch. When you are in standby, the data switch does not, repeat, does not take the transmitter encoder. It takes the receive encoder, runs down through the data switch, tells the phase lock loop what to do. You now have, at this point coming out, a receive frequency, but instead of going out the antenna, this switch goes in the up position. You have a dummy load, an internal dummy load, that's going to take the brunt of the power. You're going to run this signal up through the pre-selector filter, through an attenuator, through another part of the pre-selector filter, and then get demodulated down to the 70 megahertz and so forth and so on. The reason why is normally these two encoders are generating or telling phase lock loop what frequencies to produce, and they're normally 200 megahertz apart. But by putting the receive encoder in line on the transmit side, you now have both transmit and receive, all in the same. If you did not have the data switch switching from the transmit encoder to the receive encoder, there would be a problem. Major problem. Someone has asked me, well, what happens, why couldn't it just, taken the receive encoder and, or, cut the receive encoder out? Well, the engineers were the ones that designed it. I have no earthly idea as to why they took the receiver and not the transmitter. Might have been easier, I don't know. So that's what that data switch is. When you go from operate into standby, or if you turn it on and it is in standby, this is the path that everything takes. You can see it's just a circle. That's the reason why they call it loopback. You don't want to have it going out the antenna because it doesn't make any sense to do that. There's no way to return the RF this way. So that's the reason why that data switch is in there, to where you can put the receive on the transmit line and be able to receive it and decipher whatever it's in there. Yep. Passes the receive BCD when in standby mode. Data switch is the key. And of course, there are relays in there. You can see, there's a relay here and a relay here, and where it takes the antenna completely out of the picture. All right, so we've gone through the whole signal flow. It is pulled right out of the tech order and the way we present things. And hopefully you get an idea how everything works. You don't need to be technical, but you need to figure out, okay, where was, things like the 70 megahertz filtered with all the signals on it. Things like, where is the 70 megahertz made in the receive section? What's the data switch used for? Things like that. What is Orderwire? What frequency or what modulation technique does the hisser use? Things like that. But we use the signal flow because by associating the signal flow with what the knobs are doing, what you're doing, it makes things a little bit easier when you get your hands on the hisser, and hopefully it'll make sense at that point. So is there any questions on this? Probably a lot, but hopefully you can digest it over the weekend. Remember, I'm here all the time on Discord. Anybody? No questions?
No, sir.
No, sir.
Okay. It's a lot of information, I know. We got a lot of work there. All right, so here's what we're going to do. Stop the recording here.